the cloud. Okay, I have to let you guys know we are recording, so if you don't consent to that, you guys can always watch the recording, but otherwise we'll probably start. All right, let me close everything. Actually, all right, Chase, if people join, you have to let them in.
Sir, yes, sir.
I'm giving you co-host. And probably, I don't know, Will. Where's Will? Will's at the bottom. Okay. Okay, so we'll be covering parallel programming in Python. Oh, someone joined through. There you go. And so we'll be using the multiprocessing library. Actually, here, I'll copy this. If anybody wants the documentation, I'll put it in chat. All right. So first thing we'll cover is parallelism versus serialism. And so what is serialism? It's like traditional method of computing. If you guys have ever written anything in code, where it has one task executed after the other, and it's just one processor doing every job. So, it works in serial. It does this instruction, then the next, and the next, and the next, as you would expect. But what we want to cover is parallelism, which is, as the name suggests, it's just in parallel. So now we'll have multiple processors, and what happens is now we can execute instructions simultaneously. And these are photos I stole from the internet. But the idea is, let's say you have a large task that you want to apply to multiple things. So in this case, they want to, I guess, pay multiple employees. And why wait? Why wait to do one, then the next job, when you can just do all the jobs at once, especially if you can break down the job, such like that. So, so some examples of parallelism. For example, on your own computer, you'll have multiple processors, and it's all connected, and you can run them all in parallelism. Or in the case of, let's say, like a bigger area, such as a company, your servers, you have multiple computers, and they're all connected by a network, and they all work together in parallelism, and it's the same concept. And then we have threading versus multiprocessing. And so what is threading? We're not really going to cover threading, but it's just giving you guys some details. And its main idea is to keep jobs responsive, keep programs responsive, and does this by doing multiple jobs. For example, let's say Spotify, right? It's one like single process, but in it there's multiple threads, such as there's one playing music. There's a thread that controls, let's say you're downloading some songs at the same time. You might have a thread that controls like input and output, and even like running some of the ads. So in one process, there will be multiple threads. However, in Python, threads don't actually run in parallel, and we'll cover that in a bit. But other than that, other information you might want to know is threads. They all share memory, and because they're all within one parent process, so they share the same memory space as the parent process. And on the other hand, we have multiprocessing, which is, as the name suggests, it utilizes multiple processors, and it's intended to perform multiple tasks at the same time. And these processes have to be able to run in parallel. You can't just, multi-process whatever you want. And of course, since they're larger, they're like a bigger version, they require more time in general to spawn a process. And well, that's about it about multiprocessing. So in Python, we have something called the global interpreter lock. And the main idea of it, what essentially is that you only allow one thread to control the Python interpreter at a time. And so, which means threads in this case are locked, but processes are not. So if I try to use the annotation, so in multiprocessing, let's say you have 4 tasks, 1, 2, 3, 4. And let's say you're monitoring the activity. If you notice, this is 1, this is 2, this is 3, this is 4. So they all run at the same time, and which means they're running in true parallelism. However, if we have threading on the other hand, we have our 4 tasks. What you would actually see is, let's say one is active right now, and then the next one's active. Maybe the first one's active again, then the third one, and then the fourth one, and then they all run. So if you notice, there's no overlap, or like there isn't supposed to be. So all 4 threads might be running what we call concurrently instead of parallelism, because they're running at the same time, so it's called concurrency. But it's running fast enough that you wouldn't notice the difference that they're all working at the same time, but there's gaps. But in the end, it's not true parallelism. However, it should function for what your purposes are. And I need to clear this. Okay, but what we're worried about is multiprocessing. So what we can do is, and can you guys let me know if this is large enough? Like, can you guys, if I were to write something, let's say just write import multiprocessing. Could you guys see this?
Looks good to me.
Looks good. Also, does anyone have any questions about anything we just covered with threading, multiprocessing, parallelism, serialism?
So can I only do as many multi-processing tasks as I have cores in my CPU?
Yeah, that's the idea, and that's the first thing we can cover. Oh, someone's outside. Okay, so let's just try running this. Make sure this is the multiprocessing library should be included within Python, so there should be nothing you need to download. And we test as long as there's no errors. Okay, so it is imported. So let's just do. This is useful. This is useful just for later, but main equals main. And we can test is we can just see, check how many processors we have, number of processors. And then what we use is mp dot, I believe it's CPU count. And so we run this and we check. Okay, so we have 16 processors, which makes sense because I believe this laptop is 8 core, and in each core there's 2 CPUs. So 8 times 16. And then we can just cover that for later. And then our next thing, so how do we want to use these individual CPUs? Let me read the chat. Sure. Oh, William says zoom in a bit more. I think that's decent size. Okay, that should be good enough size. Let's cover what a process class is. So tasks, what you can do is you can assign them to a process. Like the name suggests, you have multiple processes, and then each process just has a start. We just worried about the start method, and the join method is pretty much all we're going to cover. And so, for example, let's say we have some class that's just called, do something. And for right now, let's just have it. Let's print the module name, and then name. Let's print, and we're gonna need some more libraries, and these should all come in Python. So import from OS, we'll import get PID as well as get parent process ID. Okay. Oops, from OS. Okay. So we can see what those have to. Print parent PID, and then that would be get PPID, and then one more thing we want to look at. Let's look at just the current process ID. Process ID. Get PID. So now let's run this. Let's just read what this does so far. Nope, that's the next. Define it as a module or a function. Okay, so we noticed the module name is main, which makes sense. We're just running it in main. We have a parent ID and we have a process ID. And it's important to do most of your coding within some sort of main. Otherwise, I think what the issue is when if you're using the multiprocessing library and you want to spawn multiple processes, the system has to keep track of what the parent process is. Otherwise, it won't know what's going on. And what you can end up happening is spawning like infinite processes, which is bad. So we want to keep it like constricted to a main so we know what's going on. And let's say, well, we can just count those out for now. But let's say that this is some sort of long process that you have, and we have it. Let's from time let's import two things. We'll have time and we'll have sleep. So let's say this is some sort of complex, long, like function that you want to do, and it takes so long that in the end it takes about 1 second to run. So we'll have the thing sleep for a second to like emulate a long task. Okay, and then we can define a process. We'll do a test. Process test. And how we do this is, let's first, well, let's time our stuff. Actually, we don't need to do that first. What we can do is, let's say we want to run this, do something, and let's run it. We'll run it 5 times or something. So and if you guys have any questions throughout this, just ask. So this one's 5 times. Nope. No follow processing. Process test. So all this thing does right now is run our something function 5 times. Test. Okay. So it's going to run it and then sleep and then run it again and sleep and run again. So far, this is just standard code. It's in serial. If you notice, the process ID is the same every single time because the processor will do one task and then it'll run it again, then it'll run it again, then it'll run it again. And so this time, let's actually time this. So we'll define our start time, and then we'll define an end time. And then what we can do is we can print out, let's say serial test, and we print out how long this takes. So it should be start minus end, and then we run this again. So we run again, and since it sleeps about a second each time, the total time should be, oh, sorry, end minus start. But either way, this should be, instead of -5, imagine it's 5 seconds. And then, so this takes too long, right? Especially if we end up running this, like, let's say we want to run it like 1,000,000 times. That would take bare minimum 1,000,000 seconds, which is way too slow for any sort of program. So instead, we can utilize the process class. And let's say we have 5 times. What we can do is we'll move down a bit. And then we start another loop. 5 times. And this time, each process will be called just p equals mp dot process. And each individual process, we can have a target function that we want it to run. In this case, our target function is called do something. And then normally, if let's say your function had arguments, in our case it doesn't, so we can just leave that blank. But so now what we do is we'll run 5 processes, and each one we want to start it. But then we also, let's keep track of our processes. We don't want to lose them, so we can just have processes. We just have an empty list, and then processes. And within this empty list, we will append every single process. So now what should happen is we'll start 5 individual processes, and then we'll hold on to them. So after we start every process, we want to wait for them to finish. So p in processes, we use something .join. And what the join method essentially does is just wait for the child process to finish whatever it's doing and join it back to the original parent process. Okay, so we were to run this time. And while we're here, let's also time it. Start equals time. Oh, I think we have questions. Why the process all have the same process ID? That was before with serialism. Is the same processor using we're using the same processor, so they should all have the same process ID. And now we notice once we try it in parallel, where each one creates a new process, we should see, and then let's print out the resulting time, parallel test, and then end minus start. Let's run this again. So this is the original, this is the serial. Notice all the process IDs are the same. And then down here, however, we notice, should probably leave a break. So serial takes about 5 seconds as we did before. But now with each individual process, we'll notice all the parent IDs are the same because the whole parent ID is probably the entire program. But each individual process, this one's 34210. Oh, sorry, not that one, this one. 34216, 34217, 34218, 34219. So they all have their individual processes. And then we notice the parallel test only takes about a second, which is expected because if we have all of them sleep at the same time, they should all only sleep 1 second together and then finish instead of do a task, sleep, do a task, sleep, do a task, sleep. And however, it might be kind of tedious to have to write your own process every single time and set up your loops to start a new process. So there's actually something else known as the pool class. And the idea is it's just a pool of workers. And it's a pool of workers. And then these workers, what they'll do, your workers are just, your processors. They'll pick a task, they'll complete it. And when they're done, they'll pick up another. And then, so rather than you defining your individual processes, the pool will set it up for you and it will complete the task as it sees fit. And this pool class includes a bunch of map methods. And they all pretty much do the same thing. There's like map, I think star map and apply, but they all work the same. So we'll just use like a standard map method for our example. Okay, so that's enough of the process test. Let's just count that out for now. So we can do a bool test. So we'll define a new function. And what this one will do is, well, let's define a function that we want it to do first. So we'll do a very basic factorial, where it's just with some number. And if this number is, greater than 1, return this number times itself minus like one small number. Otherwise, just return 1. So this is just a super basic, we're just using this to imitate a long function that would recurse over and over, which might get kind of annoying if you were to do this in serial. So basic factorial, like if you put in 5 times 4 times 3 times 2 times 1, yeah. Okay, and let's do an example of the pool test. So first thing I want to do, let's define a random array of numbers. So I'll use a new array, and then, okay, so now we'll import a random integer function. And so now we'll produce a random number between 1 and 10 for a blank in range. So let's do 100 numbers first of the test. And if you guys have any question about syntax or anything, you can just ask. But so what this does is this will just create a random array, 100 numbers between 1 and 10. And to prove that, let's just print out the test. Okay. So yeah, so we'll just print random numbers. And then now let's say we want to apply. Let's do so Python itself also has map functions. And the idea of a map function is that parallel results equals, what we do is we map a certain method. In this case is our factorial method, and we want to map it to test. So essentially is that in every single number of tests of this array, we're going to throw it into this function and get a result. And this makes it iterable, except we probably want just in a list form. So that should be fine. And we print out parallel. We should see that every number just turns into its factorial form. Okay, so that works. And now let's time this like we did previously. So we have start time, and then we'll have our end time. And then I don't feel like rewriting this, I just copy this. Where are we? And then let's see how long this takes. So pretty small amount, 80, I believe that's microseconds, but let's make it in a way we can read. Let's do times 1,000. So we'll have ours in the format of milliseconds, essentially. And then now let's also start another. Let's start a pool, actually. So what we can do is we have our pool equals np dot pool. And the one argument it has is how many processes, like total, do you want your pool to be available? In our case, as someone asked before, like, are we maxed out by how many processes we are? Yeah, so we don't want more than we have, otherwise it doesn't really work. So in this case, we'll set it to our CPU count. So now we have a pool that has 16 processors, and then we can apply this pool, where we can apply its map function to our list. So we'll start another. We'll just pretty much copy this. So let's bring it down here. And then this time, actually costs 0. So this time our parallel result, instead of just a normal map, we have pool.map. So it's the same idea, it's just we map this function, but this time using our pool. And then if we run it, and let's run it. So we notice, the serial test. Oh, this is parallel. Sorry about that. Parallel test. And let's also just print the results so we know they're actually the same. Print parallel. So we run the two. We notice that the results are exactly the same as they should be. But now we look at the time and we notice, oh, serial, it only takes 0.09 milliseconds. And why does parallel take 65? Isn't the point of parallel to be faster? And that is something we'll cover in a bit. But let's just try a larger number now. We were to say, run this factorial on 1,000 numbers. And this time we don't want to print it because it's in the way. And we look, okay, a slightly closer, and we keep adding numbers. Let's say we do 10,000. We notice now serial takes 6 milliseconds, parallel still around 60 milliseconds. And we're noticing like its efficiency now. And let's bring it up to, let's do 1,000,000 numbers. So let's say we have a list of 1,000,000 numbers and we want to apply this to it. And then, so now this takes a bit longer. So now we notice serial, takes 600 milliseconds and parallel is 200 milliseconds. So now we're noticing like the like cost versus benefit, like now it's actually useful to do parallel. And for fun, let's just try like 10 million. This might take a bit. So we'll just let that run for a bit. Okay, so the serial test took about 6,000 milliseconds, was about 6 seconds, and the parallel test took only 1 second. So now we're noticing when it's useful to be parallel. And if we look back at the original case of, where is that? Around right here, where the serial test only takes 0.09 milliseconds, but the parallel takes 65. And what's the reason for this? And the reason is called overhead, which we'll cover now. So the idea of overhead is just any additional resource or time it takes to perform a task. For example, like stack frames, it takes additional memory to hold each frame in the memory. Method calls, it takes time to copy over the parameters from your methods. However, usually we prefer using methods because it's useful to keep your code nice and neat. So that's like a benefit. And even something like bandwidth could be overhead. For example, like you don't account for your limitations of like how much data you can send. And so a better example of overhead would be, let's say in real life, right? Let's say you want to go down the block. You could drive a car, but then the additional overhead that you wouldn't normally account for is you have to get in the car, you have to start the car, you have to find a place to park the car, you have to lock the car, put it somewhere, and it'd probably be faster just to walk that one block. So that is a case where overhead is not worth it. However, now say you want to drive across town, walking could take you an extremely long time. Whereas driving, could be, you can cut the trip down. So that's an occasion where the overhead is worth it. And so just like anything else, the multiprocessing pool requires a lot of setup time, and the setup time would be considered overhead. And it's up to you to decide whether you would want to, whether you want to use this, you want to use the multiprocessing library. It's not necessarily worth it at all times to parallelize your code if, like your work is not that big and it's not necessary to run it. And what you end up doing is just wasting time. So in our case, the overhead, what we didn't consider is such a short amount of numbers. So we go back to, let's say, doing 10. But the thing is, length is not the only like consideration we should think of. For example, let's say we only have 10 numbers, but our function is like increasingly complex. So we have it, we can do something just like if we have an even number, now let's sleep like 0.3 seconds. And then, so now it's slightly more complex than before. And then if we notice, let's do a big number for a test. We can have it sleep 1 whole second. Actually, let's do something easier. We just have it at the beginning. Every time we run it, it sleeps 0.1 seconds as an example. And then, I don't know, 100 numbers. So now, even though the list is not very long, it's 100 numbers, it should go through that really fast. The program is increasingly complex. And in these cases, it might be worth the parallelize your code. Because if you're going to be running something so complex, you might as well run multiple ones at the same time. And let's just wait for this to finish so we can see the results. Oh, I actually forgot. You should probably, you want to close your pool after you're done with it, in case like leaks. But in our case, our thing is not that big and it shouldn't matter too much. We'll just wait for this to run. And while that's running, does anyone have any questions so far? Or are you guys all good?
Could you explain the map and then pool.map functions again?
Yeah. And well, let's just cover this really fast. So we notice even adding just a 0.1 second sleep increased the serial amount to 56 seconds. And parallelizing that only took up to 4 seconds. Okay. What Chase was asking was so a map function is something that's like built into Python. All it is you map a function over like another, like in this case, a list. So the idea is that for every value in test, we're going to put it into this function. So let's print out test so we can see what we're looking at. And then, so essentially what would happen is this first number 1 would put it in the factorial until it produces a number. 9 would put in the factorial until it produces a number. And let's just print the serial result. So in this case, I don't know how much 6 factorial is. Maybe that's correct, but I guess 3 factorial, it'd put in, outcome would be 6. You put 8 in the factorial, outcome would be this large number. You put 4 in. So essentially, as a map, it's just when you want to apply a function to every single. Another option would be like 4x in test factorial of x. So these two are like exactly the same, having a map and then like looping, iterating through individually and applying that number into the function. And so fundamentally they're the same. And also pool.map is the same, exactly the same thing. It's just instead of mapping using like the traditional like serial method that would be the Python like built-in map, the pool function has its own map and does the same thing. So now you're just mapping, but now we have a pool of processors to pick from. So it's much faster in the sense that we can pick out more numbers at once to run through. Does that make sense?
That makes sense.
More questions. It's functional. R defaults applies operations. Map basically. Oh, all right, good stuff, Will. Okay. And there's actually not much to this. Is actually kind of a short workshop. So, and because of that, there's limitations in general. So not all code is parallelizable. And the problem that you have, you want it to be able to broken down into discrete parts that can be solved simultaneously. For example, if you just had a function you were looking like a sort method, I don't think you can parallelize a sort method. There might be a way if you like define a different, but like a standard sort, such as something like basic, like a bubble sort where it goes through. I don't think that'd be parallelizable. So that's not a problem that can be fixed. And additionally, performance just generally has an upper limit on the speed up, regardless of processor count. So for example, we use annotation. Let's say we have a graph. These are your processors, and this is like your like percent of like speed up. And what it looks like, it just looks like a bunch of graphs like this. So essentially, there's a point where you can keep adding processors. Let's say you're up to like 16 here, up to 32. And you can just keep throwing as many processors as you want on the list, but it just hits a point where like functionally you gain like maybe like a 1% increase in speed up, and it's not worth it allocating 32 more processors just for this task. Yeah, if that makes sense. And then I'll clear this. And then, so what is parallelizable is, and also just uses in general. Well, it's just anything you can parallelize. If you want to, you could, because reducing time potentially saves money. For example, like you have a lot of stuff you need to run, and it might take considerable more effort to run it over an entire day versus like over 1 hour. Parallelization is good for running large models in simulations. That's something people do, which is like, I guess, the concept of supercomputers, where you have multiple processing machines at once. And it's good for handling large data sets in general. For example, I don't do any machine learning, but I know you have to like train your model, and sometimes you have to run through a big data set to train it. So instead of, you can maybe split up the data set into smaller portions and have them run in parallel, and it can just cut down your training time. And yeah, actually, that might be it. There wasn't too much to this. There wasn't too much to this workshop. It was just the basic idea of parallelization in Python. If you guys have any questions, you can feel free to ask them in the chat or speak up. But thank you all for listening. And that's probably all I have. I'll probably stop recording now.